So these new derivative rules are awesome. I mean, as evidenced by the fact that I called a handout that has them on it your bestest friend. So the examples we looked at so far are all, what we would have called polynomials. So in the grand scheme of things, I mean, even if you'd had to calculate the derivatives using the limit definition, there's a fair amount of algebra to it, but it wasn't unworkable. What I want to take a look at, for now, is some more complicated examples and see how the differentiation rules on the bestest friend are so helpful for us. So let's take a look at this guy. So we have 5 over x to the third plus, what I was getting ready to write there. All right. The cube root of x squared plus the square root of x cubed. All right. So now you might be looking at this and saying, okay, that's not quite a polynomial. The power rule thing before was really great, but how do I handle these things? There's technically a way that we're going to end up seeing later for dealing with this. Spoilers, don't just tell me that it's 5 over 3x squared, or also don't just tell me it's 0 because the derivative of the numerator is 0. Don't do that. What we're going to do is a bit of algebra first, sort of to reconfigure this, so it turns out all three of these things actually are power functions, and that same power rule is in effect. So, for what it's worth, if we take something in the denominator and move it to the numerator, we have to change its exponent from positive to negative. So this is the same thing as 5x to the negative third. Also, we've talked about this before, root expressions like this can be expressed using fractional exponents. So this is plus x to the, remember, inside, over, as you say, the root is in the bottom of the fraction in that instance. So we have x to the 2/3 plus, here we have x to the 3. Remember, unlike just about any time else in a math context, if there's no number given here, that's a square root, a second root. So we would have x to the 3/2. So now, using our buddy, the power rule from the bestest friend sheet, the negative 3 hops out front, and we'll have to multiply by 5. So we have negative 15 x to the negative 4th. He just hops out front right away. There's nothing to multiply onto him. 2/3 minus 1. So that's going to give you a negative 1/3. So plus, repeating the power rule process here, 3/2 hops out front. I subtract 1 from 3/2. 3/2 minus 2/2 leaves me with x to the 1/2. Now, at this point, the calculus is technically done, but you can actually clean it up a bit if you like making it look a little prettier. Some folks think negative exponents are kind of bad form, so negative 15 over x to the 4th. So 2 over 3 times the cube root of x when we hop that negative 1/3 down below and then turn it into a cube root. And then here we would just have like 3/2 squared of x, or 3 times the square root of x over 2 if you prefer. Again, technically the calculus is done, one way or another. It's just a matter of algebraic cleanup. All right, so I want to take a look at another, similar situation. Give me a sec to erase this. All right, so here we've got a rational function, x to the 4th plus 9x minus 3 all over x squared. Again, if you go poking around on the bestest friend sheet, there are different ways you can handle this, but it turns out I think the most elegant way of dealing with it is to, like last time, do some algebra beforehand. So split this fraction up into 3 separate pieces. 9x over x squared plus 3 over x squared. So we've got each term living over that denominator of x squared. And then we clean things up as best we can. X squared plus that should have been a minus. My apologies there. Note that was a negative. It should have been a negative. My bad. So x to the 1 minus 2. So we have x to the negative first minus 3x to the negative second. And now again, we can just use the power rule to pound out what happens here. So we get 2x out of the first guy, pull the negative 1 out front, minus the negative second. Negative 2 hops out there, and we get plus 6 times x to the negative third. And again, if you want to clean this up and write this as 9 over x squared plus 6 over x cubed, that's fine. But again, the calculus is done at this stage. There's sometimes you might want to try to put stuff back together, but it's not completely necessary. So what happens if there's not a power function present at all? That's an excellent question. Yep, no power functions in sight. You might be saying, well, wait a second, I see like exponents. Remember, those aren't power functions. The x is up in the exponent. Those are what we call exponential functions. So they play by different rules. Don't tell me the derivative of this thing is 4x times e to the x minus first. No, just no. So poking around, looking on the Vestas friend sheet, you may notice we get down to on the back page, second on page 2, we see on our derivatives of specific functions, e to the x is sitting in number 10, and he should be one of your favorites. So most people seem to end up remembering the power rule, but I find it particularly awesome that the derivative of the exponential function e to the x is e to the x again. So he just kind of sits there. So he just grins at you, and you don't have to worry about changing anything. So when we calculate h prime of x for this function, we have a 4, constants hop around out front just fine, and the derivative of e to the x is just e to the x. Cool. This guy here, 4 to the x, he's also an exponential function, but if you'll notice sitting right underneath that particular rule, we have something for exponential bases that aren't e. So if you'd ever, if you've been one of those folks who complained about, why is e sort of this weird number, like why is it a thing? Part of why it is a thing is that it makes the calculus so nice and pretty, because if we take a derivative of an exponential function that's not base e, then we get an extra term kind of tacked onto this. So we have 4 to the x times the natural log of the base. 4 to the x ln of 4 in this instance. So again, that also ends up specifying why we call this the natural logarithm in math classes, because if you take a look at rule number 9 on the Vestas friend sheet, the derivative of the natural log function is also really pretty. If you're dealing with a different base log, like you're dealing with pH stuff in chemistry, or you're a seismologist working with the Richter scale when you've got base 10 logs, the derivative of those things is not quite as clear cut. The derivative of the natural log function is just 1 over x. So we have 10, the constant, times 1 over x, our derivative. Or, like I said, I would prefer to represent that simply as 10 over x. So we're done in that instance. So, like I said, neat. It cleans itself up really nicely. All right, what about the trig functions, Professor Carroll? I'm glad you asked, hypothetical student used as a rhetorical device. So we have here a combination of some trig functions, cosine of theta, sine of theta, mixed together, you get the idea. And we want our derivative. Again, looking at the Vestas friend sheet, we can see what the derivatives of these guys are individually and just kind of play along. So the derivative of cosine of theta is negative sine of theta. I really do prefer to put like brackets around that, or to go ahead and write the negative out front. Every now and again, I'll have students who just write 5 minus sine of theta, and then they forget and assume it's a subtraction later. It's not. Those things are multiplied together. Anyway, so minus 3, the derivative of sine of theta, according to the Vestas friend sheet, is in fact the cosine function without, a negative. So, and you can clean that up, then you get, negative 5 sine of theta minus 3 cosine of theta. All right, so pretty straightforward. Let's take a look at one more real quick using a couple more trig functions. So we have 6. Let me give the function a name. That always bugs me when it's just hovering there. So we use f of t this time. So we have 4 secant of t, so plus 8 tangent of t. All right, so again, it's just combinations of different trig functions, so we can invoke the separate, derivative rules, from the Vestas friend sheet. So f prime of t in this instance, the derivative of the secant function, as it lists, is secant of t times tangent of t. So this is a good time for me to point out, just as a reminder, don't just write secant tangents or sectan or whatever. Yeah, these things actually do in fact have arguments. So that's a thing. So for secant of t tangent of t, that comes from this first guy. The derivative of tangent of t in that back term is secant squared of t. So all right, so that's I technically haven't done an example using the cosecant or the cotangent functions. They play by the same rules. Just each of those, when you take the appropriate derivative, you end up popping up a minus sign, kind of like we did when we went from the cosine function to the sine function. You'll sometimes hear professors who aren't quite kind enough to just let you have a bestest friend when you're working on stuff. They tell you to remember that if you take the derivative of the trig function that starts with c, you've got to change the sign of your derivative because change starts with c. So that's a mnemonic that your friend, your bestest friend, means you don't necessarily need to commit to memory. All right, I'm a little short on time here. I've got a couple more things I want to address, so stay tuned.